Okay, welcome to the second of three videos on section 12.2 in your textbook entitled Evaluating Limits. In this video, we're going to begin by talking about using technology. And this becomes necessary when evaluating limits by direct excuse me. Using technology becomes necessary when evaluating limits by direct substitution, by dividing out, and by rationalizing techniques no longer works. All right. And so if these techniques don't work for finding limits, especially of non-algebraic functions, you may have to use your magic number box in order to find the limits of these types of functions. What does that mean? All right, well, essentially what you're going to have to do is use your TI-84 or 85 or 89 and graph the function. Now, if you don't have a graphing calculator, you can always go to the website graphsketch.com. All right, this is a wonderful little tool and technique. It is the one that I use for the pictures that you'll see in, of the graphs that I show in this video. All right, so use that, or if you don't have a graphing calculator to start all of this with. All right. So let's again begin by example, and so we're going to start here today with example number 4. For those of you who are familiar with logarithmic and natural log functions, you may recognize this immediately as the definition of the natural log, or the variable e. But if you don't recognize this off of the top of your head anyway, let's go through and find the limit here. All right, the limit as x approaches 0 of the quantity 1 plus x all to the 1 over x power. All right. And so looking at this, you may be just like, oh my God, what do I do? Plugging in various numbers here, you're going to end up, obviously, if you are trying to find the limit as x approaches 0, this term just disappears. You're left with 1 to the 1 over 0 power. But how is that possible? Well, it turns out that the easiest way to look at this is to use the graphing function on your calculator. Now, I drew this graph using graphsketch.com, and you can see that as x approaches 0 from the left and from the right, y is approaching this point here. And it turns out, again, if you recognize that particular function, e is equal to approximately 2.7183. All right. Now, I don't expect you to memorize this or to know it off the top of your head, but the tracing function on your calculators will allow you to figure out exactly what point this is. And so the point is 0, 2.7183. Okay, that's this point here. All right. And again, trying to do that algebraically is going to be a pain right in the keister. But trying to do this, using a graphing function is much, much easier, in my opinion. Okay. All right. So that's where we will leave example number 4. Now, how about example number 5? Well, in this case, you're asked to find the limit as x approaches 0 of the sine of x over x. Now, immediately you should realize that this is going to give you an undefined term if you simply try to do it by direct substitution. All right, you can't rationalize this. There's no dividing out technique, so neither one of those things is going to be useful. right? None of these things is going to be useful. None of the techniques that we've talked about thus far. So what do we do instead? Well, let's turn to our graphs, all right? The easiest thing to do in this case is to go to your TI-84 and plug in the function sine of x over x and see what the value of y is when the value of x is 0, all right? It's kind of like just direct substitution, but no algebra, no arithmetic involved, just kind of looking at the picture. And so if you do this graph, and this is from graphsketch.com, you'll see that as the value of x approaches 0, right, here, this line, the y-axis, is x equals 0. So as x approaches 0 from both the left and the right, the negative side and the positive side, the value of y is approaching this point right here. And so this point is obviously 0, 1, all right? But what we've got here is the limit. And so the limit in this case is 1, okay? As x approaches 0, y approaches 1, okay? All right. Questions or issues or difficulties with this? All right. So before we move on to the next topic, if you will, what I do want you to realize is that in every one of these examples, especially the ones that I've done with graphs, I've drawn these arrows as along the x-axis as x approaches 0 from the left and as x approaches 0 from the right. Now, from the left is the negative side, and from the right is the positive side. And so what I can do in addition to evaluating limits graphically or by direct substitution or by rationalizing any other method is I can also look at the limit as x approaches 0 from the left side and the limit as x approaches 0 from the right side. Now, the plus and minus don't mean positive and negative in all cases. Right? In this case, it's true. But when you write the negative or positive sign with the limit, what you're really saying is you're approaching from the negative side. It might still be a positive number, right? But it's from the left side of the graph. When you write the little positive sign here, what you're saying is you're approaching the limit from the right side, from the more positive side of the graph, okay? And so keep that in mind, all right? Keep that in mind. Because what happens here is that you can approach a certain value of x from both sides and actually approach different values of y. And what that's referred to is a one-sided limit, which is our next topic. So what exactly is a one-sided limit? Well, it turns out that if you don't approach the same value of y from the left and from the right, then the limit doesn't exist, all right? So limits can fail to exist when a function approaches a different value of the left side from the left side of c than it approaches from the right side of c. If that's the case and the limit doesn't exist, then you just, you throw your hands up, you give up, you go home, you quit, right? You're wrong, all right? We're mathematicians here. We never quit. And so instead, what we're going to do is we're going to try to use what we call one-sided limits to describe the behavior of a given function. All right. So this type of behavior can be described better with what we call a one-sided limit. Okay, a one-sided limit. All right. So again, likely the best way to describe this stuff is through example. All right. And so that's what we'll do now. Example number 6. Here, you're asked to find the limit as x approaches 0 from the left and the limit as x approaches 0 from the right for the function f of x equals the absolute value of 2x all over x, okay? So if you go to approach this from, we'll start with the left, the limit as x approaches 0 from the negative side, all right? What it turns out that in this case, whoops, the limit is going to actually approach a value of -2, okay? And if you think about it, it should hopefully make sense, all right? Because if you plug in, for example, -2 here, you get 2 times -2, which is -4, but its absolute value, so it's +4, over -2 is -2, okay? If you plug in -1, 2 times -1 is -2, absolute value of that is 2, over -1 is -2. All right, and so the limit from the left side is -2. Now, what about the limit from the right side? Well, the limit as x approaches 0 from the right, in this case, of, again, the absolute value of 2x over 2. All right, if I start with x equals 3, 2 times 3 is 6, absolute value of 6 is 6, divided by 2, divided by x, that's dummy. So 2 times 3 is 6, divided by 3 is +2. 2 times -2 is -4. Take the absolute value, that's 4. 4 divided by -2 is, 4 divided by 2 is 2. 2 times +1 is 2. All right, divided by 1 is 2. And so you can see that from the left, we're approaching -2. From the right, we're approaching +2. Essentially, if you were just to calculate this limit as x approaches 0, the limit does not exist because it's approaching 2 different values of y from the left side and from the right side, respectively. So what we do instead is we calculate the one-sided limits like we've done here, and that gives me the limit from the left and the limit from the right. Now, just quickly, if you graph this, this function, you'll end up with a picture that looks like this. Now, Graph Sketch does weird things here. This vertical line shouldn't be in the graph. There are no values between here and here. But notice that as I approach x equals 0 from the left, and x equals 0 from the right, all right, I'm approaching +2 from the right and -2 from the left, all right? And so the limit itself doesn't exist, but the one-sided limits, the two one-sided limits do exist. Okay, so that is going to conclude the end of the second of 3 videos for section 12.2, and I hope you learned something.